and welcome to part 2 of our discussion of transmission lines. We're going to pick up right where we left off at the end of part 1, starting with a look at some example transmission line configurations used in the real world. Let's start with coaxial cable. We derived this expression for inductance per unit length in the magnetic field session, and we derived this expression for capacitance per unit length in the electric field session. From the discussion in part 1, the speed of propagation is equal to 1 over the square root of LC. When we multiply L and C, the natural logarithm terms cancel, and the 2 pi terms cancel, leaving simply mu epsilon. Thus, the geometric dependence cancels, leaving only the bulk material properties of the dielectric between the conductors, permeability and permittivity. Now we set the speed of propagation equal to 1 over the square root of mu epsilon. We expand mu and epsilon into their relative portions and their baseline values for free space, mu naught and epsilon naught, factor out the relative terms, and from our session on Maxwell's equations, we see that the second term, 1 over the square root of mu naught times epsilon naught, is equal to the speed of light in free space, c. So the speed of propagation on our transmission line equals the speed of light in free space divided by the square root of mu sub r times epsilon sub r. We will come back to this presently. Assuming a lossless line, the characteristic impedance Z0 is equal to the square root of L over C. Looking first at L over C, we get mu over epsilon times the square of 1 over 2 pi times the square of the natural logarithm term. To get Z0, we take the square root of this expression to get the square root of mu over epsilon times 1 over 2 pi times the natural log of b over a. As before, we expand out mu and epsilon, factor out the relative terms, and again recalling from the Maxwell's equations session that the square root of mu naught over epsilon naught is the characteristic impedance of free space, approximately equal to 120 pi or 377 ohms. The 120 pi will combine with the 1 over 2 pi term to give this expression for the characteristic impedance of a coaxial transmission line equal to the square root of mu sub r over epsilon sub r times 60 times the natural log of b over a. Here is a graph of this expression for various values of relative permittivities, or dielectric constants, and a relative permeability of 1, given that most dielectrics used in transmission lines are non-ferromagnetic materials. The impedance is clearly determined by the dielectric constant and the geometry as a function of conductor separation and size. Typical impedance values for coaxial cables are 50 ohms and 75 ohms. 50 ohms in particular is a standard value used by a lot of commercially manufactured coaxial cables, including RG58CU cable that is very common for lab use and that we will be using in a couple of demonstrations coming up. You will get very familiar with this 50 ohm number if you are not already. Moving on to parallel wires, here are the expressions for inductance and capacitance per unit length that we derived in previous sessions. Again, when we calculate the speed of propagation, the geometric dependence cancels, and we are left with C divided by the square root of mu sub r times epsilon sub r. You should be sensing a pattern here. We take the square root of L over C to get this expression for the characteristic impedance of a parallel wire transmission line. Here's a graph of this expression for various dielectric constants and a relative permeability of 1. Again, the impedance is clearly determined by the dielectric constant and the geometry. Typical impedance values are 50 ohms, 75 ohms, and 100 ohms. Our last example is a wire above a ground plane. Here are the expressions for inductance and capacitance per unit length, and again, when we calculate the speed of propagation, the geometric dependence cancels and we get the same expression as before. So the third time's the charm. We'll take the square root of L over C to get this expression for the characteristic impedance of a wire above a ground plane. Here's a graph of this expression for a relative permeability of 1 and a dielectric constant of 1 for the typical example of an air dielectric between the wire and the ground plane. Due to the logarithmic relationship, note that for large separations, when the height to wire radius h over a is above about 10, the impedance does not change much. One example worth noting is that Mil Standard 461 specifies cables to be mounted at a height of 5 centimeters above the ground plane. For a typical wire radius on the order of half a millimeter, that gives an h over a ratio of about 100 and a characteristic impedance of about 300 ohms. This is a good ballpark value for estimating the characteristic impedance of that configuration whenever it may be needed. As we just saw, the velocity of propagation u on a lossless transmission line is independent of geometry, and it depends only on the material properties of the dielectric. When we expand out those material properties, permeability and permittivity, and factor out the relative terms, we see that u equals the speed of light in free space c divided by the square root of mu sub r times epsilon sub r. Most dielectrics used in transmission lines are non-ferromagnetic materials with a relative permeability of 1. In those cases, u equals c divided by the square root of the dielectric constant. We can rewrite this as u over c, the fraction of the speed of light, equals 1 over the square root of the dielectric constant. Many transmission line datasheets will provide only this relative velocity number, either as a fraction or as a percentage, and may not provide the dielectric constant directly. But knowing this relationship, you can back that out if you need it. The exact value of the speed of light in free space is this 9-digit number, which you are more than welcome to memorize, but we generally approximate it as 3 times 10 to the 8th meters per second, and this is generally sufficient for most practical applications. It can also be written as 30 centimeters per nanosecond, or about a foot per nanosecond. Recalling that the wavelength lambda equals the velocity of propagation u divided by the temporal frequency f, we can substitute the expression for u above to show that wavelength equals 1 over the square root of the dielectric constant times c over f. We plug in 3 times 10 to the 8th meters per second for c, and we get that the wavelength approximately equals 1 over the square root of the dielectric constant times 300 divided by the frequency in megahertz. Doing the dimensional analysis, we have megameters per second in the numerator, and we have megacycles per second in the denominator. The per second terms cancel, and the mega terms cancel, leaving meters per cycle, which is the wavelength. For an air dielectric, the dielectric constant is 1, and the speed of propagation is equal to c. In this case, the wavelength equals 300 divided by the frequency in megahertz, which is the same as the relationship for a plane wave propagating in free space. For a typical dielectric, such as Teflon, the dielectric constant is generally in the range of about 2 to 2.5. In these cases, the speed of propagation is approximately 2/3 of the speed of light, and the wavelength is approximately 200 divided by the frequency in megahertz. Note that this is an approximate value, but it is a good rule of thumb to use as a starting point in many cases, and it facilitates quick estimates of wavelengths at frequencies of interest. This can come in quite handy in the lab in a troubleshooting situation when you are trying to make sense out of what you are observing. Let's look at a transmission line defined by its propagation constant gamma and its characteristic impedance Z0. When we apply a signal at the source end, we'll get voltage and current waves traveling in the plus Z direction. We'll call our voltage V plus of Z equal to the amplitude V0 plus times e to the minus gamma Z, and we'll call our current I plus of Z equal to the amplitude I0 plus times e to the minus gamma z. The negative exponents indicate that the waves are traveling in the plus z direction. If our transmission line continues out to infinity, then our voltage and current waves will also continue out to infinity and live happily ever after. While I love a happy ending as much as anybody, this is not terribly useful and it never occurs in real life. A real-world transmission line has some finite length L and terminates in some load impedance ZL. In addition to voltage and current, we need to think about power. Our transmitted power is equal to I plus of Z times V plus of Z, which is equivalent to I plus of Z squared times Z naught, or V plus of Z squared over Z naught. At the load, the potential must equal the current at the load times the load impedance. The power received at the load equals the product of the current and potential at the load, which is equivalent to I squared of Z and V squared over Z at the load. Given that potential loves a high impedance, if the load impedance is higher than Z naught, you can achieve the desired potential across the load all day long, but you can't establish the desired current through it. And given that current loves a low impedance, if the load impedance is lower than Z naught, you can achieve the desired current through the load all day long, but you can't establish the desired potential across it. In either case, the full transmitted power is not transferred to the load, which means that some of that power is reflected back toward the source. Terminating with a matched impedance ensures maximum power transfer to the load. For a mismatched load, we have two basic questions. What fraction of the incident or transmitted wave is reflected? And what is the apparent input impedance Zin observed at some distance from the load? To address these questions, we will be using some math, but I encourage you to stick with me because we will arrive at some extremely useful and powerful results. And I think they will be a lot more meaningful and easier to remember if you see how we get there. And a lot of it really just comes down to algebra and substitutions. So, fasten your seatbelts and let's go for a ride.
I like to dream, yes, right between the sound machine. On the cloud of sound, I drift in the night. Any place it goes is right. Goes far, flies near, with the stars away from here.
Here are the expressions we defined for our transmitted voltage and current waves traveling in the plus Z direction. The reflected voltage and current waves will be traveling in the minus Z direction. V minus of Z equals the amplitude V naught minus times e to the plus gamma Z, and I minus of Z equals the amplitude I naught minus times e to the plus gamma Z. The positive exponents indicate that the waves are traveling in the minus Z direction back toward the source. The potential at any point Z is the sum of the potential contributions from the transmitted and reflected waves, and the same is true for the current at any point Z. Recall our workhorse equations for the derivatives of potential and current. We take the negative of the derivative of our expression for V of Z on the left side of the first equation, and we can make the substitution for I of Z on the right side. We multiply through by R plus j omega L, and we compare the coefficients of like exponential terms. Looking at the e to the minus gamma Z terms, we see that their coefficients must be equal, and we rearrange terms to see that V naught plus over I naught plus equals R plus j omega L over gamma, which equals the characteristic impedance Z naught from our earlier discussion. Similarly, we look at the e to the plus gamma Z terms, see that their coefficients must be equal, and rearrange terms to see that minus V naught minus over I naught minus also equals R plus j omega L over gamma, which again equals Z naught. We apply a similar set of steps to the second equation to get an expression of V naught plus over I naught plus equal to gamma divided by G plus j omega C, which also equals Z naught from our earlier discussion, and minus V naught minus over I naught minus, also equals gamma divided by G plus J omega C, which again equals Z naught. The net result of all of this is that V naught plus over I naught plus and minus V naught minus over I naught minus both equal the characteristic impedance Z naught. Now we have this equation along with our equations for potential and current. We rearrange terms to put them in terms of I naught plus and I naught minus, and we substitute these expressions into our current equation. We are interested in the potential at the load, which we will call VL. The load is at a distance of Z equals L from the source, so we substitute L for Z into our expression for V. Similarly, we will call the current at the load IL, and we will substitute L for Z in the equation for current. We'll also note that VL over IL must equal the load impedance ZL. We multiply both sides of the current equation by Z naught, and now we have a pair of equations that will let us solve for our pair of coefficients V naught plus and V naught minus. When we add these equations, the V naught minus terms cancel, and we can solve for V naught plus. We see that VL over IL equals ZL, and we can make that substitution to get V naught plus equals IL over 2 times ZL plus Z naught times e to the gamma L. When we subtract these equations, the V naught plus terms cancel. We can solve for V naught minus, which equals IL over 2 times ZL minus Z naught times e to the minus gamma L. Now we have these expressions for V naught plus and V naught minus, and we can substitute them into our equation for V of Z. Recall that I naught plus equals V naught plus over Z naught, and we'll substitute our expression for V naught plus that we just derived. And recall that I naught minus equals V naught minus over Z naught, and we'll substitute our expression for V naught minus that we just derived. And now we'll substitute these expressions into our equation for I of Z. Note that the terms L and Z have combined to put L minus Z into all of our exponential terms. This term L minus Z is the distance from the load, which we will call Z prime. This is precisely what we are interested in because we are ultimately looking to characterize the behavior of our waveform as a function of the distance from the load. Therefore, we will substitute Z prime for L minus Z in both equations. We'll come back to these, rest assured. For the moment, we will factor out ZL plus Z naught times e to the gamma Z prime to give us this pair of equations for V of Z prime and I of Z prime. The 1 in each set of brackets represents the original transmitted wave, and the exponential term in the brackets represents the reflected wave. Thus, the coefficient of the exponential term in the voltage equation is called the voltage reflection coefficient for the load end, and in the current equation, it is called the current reflection coefficient at the load end, designated by the capital Greek letter gamma. Performing the identical analysis at the source end gives similar coefficients, simply substituting the source impedance ZS for ZL. These reflection coefficients are used all the time when working with transmission lines, and they are worth remembering. And I hope that walking through the analysis helps you remember them more easily. Focusing on the voltage reflection coefficient at the load end, let's look at a couple of examples. For a short-circuited load, when ZL equals 0, the voltage reflection coefficient is -1. The potential at a short-circuited load is 0, which means that the reflected wave cancels the potential of the incident or transmitted wave at a shorted load. For an open circuit load, when ZL is infinity, the voltage reflection coefficient is 1. The potential at the load will be double the potential of the incident wave, which means that the reflected wave doubles the incident potential at an open circuit load. The opposite relationship holds for current reflection coefficients. In general, the reflection coefficient may be a complex number, including magnitude and phase. When you have reflections on a mismatched transmission line, you will set up standing waves on the line, and a key parameter for describing them is the voltage standing wave ratio, VSWR, which you will sometimes hear pronounced as a word, VSWR. It is defined as the ratio of 1 plus the magnitude of gamma over 1 minus the magnitude of gamma. Basically, it gives the ratio of the maximum to minimum amplitudes of the standing wave. Some datasheets for antennas or other equipment may not provide a load impedance or a reflection coefficient directly. They may only provide numbers for VSWR, generally in a graph as a function of frequency. In these cases, some simple algebra will allow you to back out the reflection coefficient if you need it. Now let's see how mismatched transmission lines and reflections look on some real signals. This is a simple setup that I encourage you to try in your own lab, consisting of a signal generator, an oscilloscope, and an intentionally uncontrolled transmission line made from a couple of wires that I didn't even bother to twist together, with a length of about 4 feet or about 1.2 meters. I have set up the signal generator to provide a 5 MHz square wave with an amplitude of 3 volts peak to peak into a 50 ohm load, and rise and fall times of 4 nanoseconds. Because the dielectric between the wires is mostly air, the speed of propagation will be approximately the speed of light, and the wavelength will be equal to 300 divided by the frequency in megahertz. For our 5 MHz fundamental, the wavelength is about 60 meters. Our line length is about a 50th of a wavelength, so the fundamental will not be affected. However, we still need to consider the rise and fall times. Here, it is helpful to remember that the speed of light can be written as approximately a foot per nanosecond. Our line length of 4 feet means that it will take about 4 nanoseconds for our signal to travel from one end to the other. That travel time is right in the ballpark of our rise and fall times of 4 nanoseconds. We should certainly expect those to be affected, and we're going to take a look right now. With our scope first set to the 1 megohm termination, the waveform looks very ugly, and it is barely recognizable as something intended to be a square wave. This would be essentially unusable as a digital signal because it would likely cause many bit flips. It would be even worse to use as a clock signal because it would almost certainly cause spurious clock transitions that could completely freeze up a state machine. When we set the scope to the 50 ohm termination, you might argue that the signal looks slightly better, but there is still some noise on the plateaus that could cause bit flips, but worse, there are glitches on the transitions that could cause hiccups. Again, this is bad enough on a digital data line, but significantly worse on a clock line. Now let's hook up a proper transmission line, a piece of RG58 coaxial cable with a controlled characteristic impedance of 50 ohms. With the scope first set to the 1 megohm termination, the signal looks better, but there is still some noise on the plateaus. With the scope set to the 50 ohm termination, now we're talking. This is a nice clean signal that will enable our circuit to work consistently and reliably, which is exactly what we want. And note that we did not change anything in the signal source. It was all about improving the quality of the interconnection to make it a proper transmission line, and providing the proper termination in the transmission line's characteristic impedance, which in this case is 50 ohms. Clearly, impedance mismatches can cause reflections and distortions of the desired waveform. Reflections can occur at both the load and the source ends. In digital systems, these reflections can cause bit errors and spurious clock transitions, and they can completely freeze up a state machine. The rise and fall times are a much greater concern than the fundamental frequency. For interconnections that are longer than 1/10 of a wavelength, they will behave as transmission lines. You need to use a controlled characteristic impedance, and you need to terminate with a matched impedance for the interconnection to work properly.
Through the mirror of my mind, time after time, I see reflections of you and me. reflections of the way life used to be, reflections of the love you took from me.
This gives you a look at what signals can look like in the time domain when you don't pay attention to transmission line effects and when you don't provide proper terminations. In part 3, we will look at a demonstration of what signals can look like in the frequency domain, along with some theory, and yes, that means some more math. But I encourage you to stick with me because the results are extremely useful and powerful, and I would call them indispensable. And as I said before, it mostly comes back to algebra and substitutions. See you in part 3.
You think we look pretty good together. You think my shoes are